This video is going to discuss the limit and the limiting process. We have somewhat seen a limit already, but let's talk about it in a certain context. So a population of deer with finite resources can be modeled according to that given equation. N of t denotes the number of deer on a certain month t, and we want to know what is the maximum number of deer the environment can support. If it exists, if it doesn't, then we can say that as well. And another way of thinking about this is if time increases without bounds, so it gets very, very large, so 100, 200 months, 300 months, however long, what number does the deer stabilize around? That may or may not occur again, but let's explore. The first way that we can tackle a problem like this is, well, we're given a function and we can generate a table of values. And so there's a numeric approach. So I could make a table that contains the variable t. Again, t is number of months, and n here, I'm using n instead of n of t to denote the number of deer. So if I start plugging in values at 0, okay, so time can't be negative, so we start at 0. If I put in 0 for t into this equation and solve for n, I get 166.667, and 10 months be 288 or so, 20 months 393, and then I can continue. And if we go down and go through the table of values, I made this table using Excel. We can see that as the time increases, the number of deer, okay, it gets close to 497, 499, and then at 499 it gets closer, and now Excel says by 150 months it's at 500, and so it looks like it would continue, and we could even go back into Excel and extend this table further. But right now, Excel is telling us that it's approaching 500 deer. Okay, so that is one approach for answering a question like this, is to tackle it numerically. A second approach might be to make a graph of it. Okay, so this is a function. I can, if I were to put this into Wolfram Alpha or another graphing utility, it might require me to use x instead of t, and then for n of t I might have to use y. But I could plot this function, and I would see that as time increases, so time would be on our horizontal axis, and n of t, or the number of deer, is on the vertical axis, we get that same sort of behavior. So as time increases, number of deer tends to approach about 500 deer. Okay, so exploring a question like how it behaves over time. Okay, at what number does the number of deer stabilize around? I can look at it numerically or graphically. And of course there is a third way, which is algebraically. Okay, and algebraically we actually have to think about the end behavior. Okay, so end behavior is what happens to the function in the long run. So as t gets arbitrarily large, okay, like millions, billions, etc., what happens to the number of deer? Okay, well, we know that if we look at e to the x, okay, so if I just have a function, call it e to the x, and I look at that, as x increases, so as x gets very, very large, e to the x gets extremely large as well. Okay, so now if I reverse that, if x goes to minus infinity, then e to the x, minus infinity, then e to the x approaches approaches 0, so that actually gets depleted completely. If I have something where I take the opposite, so if I have another function, say g of x, this is equal to e to the minus x. If I take that now, that would actually, so if x goes to infinity again, that number x gets arbitrarily large, but e to the minus x, okay, which is equal to 1 over e to the x, that actually goes to 0. Okay, so algebraically we can go through more formal arguments once we know a little bit more about the limit. But we can actually say that this value down here approaches 0. So really what this means to us is that if t goes to infinity, n of t is going to go to 500 over 1 plus 2 times 0. And 2 times 0 is 0, and then simplifying this, I get 500. Okay, and then labeling this in context, it would be deer. So we think that over time, we've shown it algebraically now, and graphically and numerically before, but we think that the number of deer that the function stabilizes around, and therefore the number of deer that the environment can support, is 500. Okay, so what this means to us in this context, and when we are trying to formalize this with some mathematical terms, we say that 500 is called the limit. Okay, the limit of n of t. And you may also hear the terms stabilization value or steady state. Steady state just refers to what does it approach as time gets arbitrarily large, or what does it stabilize around. Okay. Now, interpreting this mathematically, what this means to us is, again, the same language that we've been using. If t increases without bound positively, so t would approach. When we have an arrow, that means approach. When t approaches infinity, so it gets close to that, or it gets bigger and bigger and bigger in this case. Capital T, and this should actually be, we're talking about n in this case, the number of deer. So please make this change. N of t approaches but does not reach 500. So even though, remember, in our first exploration method, when we had the table of values, and Excel said it was 500. It isn't actually 500. It's really, really close to 500. Excel just rounded it due to the decimal places that were available. So it approaches 500, but it will actually never reach that value. So 500 is a limit value, and the way to communicate this mathematically is with this nice short, complete notation. So we say the limit as t approaches infinity of n of t is equal signs 500. Okay, and so that's our introduction to limits and the limiting process.